Hey, I want to talk about differentials. They do have some applications, which I will mention extremely briefly, but we will mostly be interested in them for the notation, which will be very useful in our continued study of integration. So start with a function y of a variable x. And if we pick a specific point x on the x-axis, we know how to construct the line tangent to the curve at that point x. And then if we pick some point a small distance h away from x, the point x plus h, then we can call that distance along the x-axis delta x, the change in x, or in calculus terms, dx. And in that case, the distance dy is the change in y for the tangent line. And since dy over dx is the change in y over the change in x, or the slope of the tangent line, and the slope of the tangent line is the derivative at x, we have that dy over dx is equal to f prime of x. And this is something that we already knew, but we knew it in terms of these were two different notations for the same thing. Here, if we consider f prime of x to be the slope of the tangent line at x, this picture and this concept explains why f prime of x really is equal to dy over dx, assuming we define dy and dx as we have in this picture. And what we're really going to be interested in here is coming up with an expression for dy on its own, which we do by multiplying both sides of that equation by dx, so that we get that dy is equal to f prime of x times dx. This is what we'll call differential notation. I want to contrast the value we were just looking at, dy, the change in y of the tangent line, with the value delta y, the change in y of the original function. They're obviously not the same thing, and the difference between delta y and dy is often used in practical applications where we're trying to estimate errors. So that is a practical application of differentials. We will not be studying it at all. I just wanted to mention it. What we will be interested in is the notation, the differential notation. Let's look at a quick example. Take this function f of x equals x to the fifth plus 12x. It's very easy to compute the derivative. Dy dx is 5x to the fourth plus 12. And so in differential notation, we have that dy is 5x to the fourth plus 12 times dx. We're going to be doing this a lot as we get more sophisticated about our integration, and we're going to get to the point where we skip this middle step right here and go straight from the function to the differential notation. In other words, if f of x is x to the fifth plus 12x, then you immediately know that dy is 5x to the fourth plus 12 dx without needing to write the derivative out explicitly in the middle as we did here. If it helps while you're getting used to it to write the derivative out explicitly, then certainly go ahead and do it. Eventually you'll get comfortable with the differential notation and be able to go straight from the function to dy equals something times dx. That's it. Differential notation, short and sweet. We'll be using it quite a bit very soon. See you in the next video.